Welcome back to the session. So we will discuss Laplace transform of periodic function. We have seen Dirac delta function, unit step function, now the turn for the periodic function. This is the most beautiful function. So how the function will maintain the period. So let us see the picture first. See this one. The function maintains a period. I am drawing another function. Now you notice from here I have started. Okay. So after traveling some distance, you notice this kind of position, and after traveling some distance, again that repeats. Okay, as if this is a pattern. Okay, we wear clothes in patterns. Okay, as if this function maintains a pattern after certain distance. Okay, here is the function and here is the variable. Okay, what is this? This is called sine function, and sine function repeats after a distance of 2 pi. So this is called a periodic function. After an interval of 2 pi, the function repeats again and again. The same behavior is again appearing. That's why it is called periodic function. So we write the function f of x equal to sin x, and this is a periodic function. Now you notice this another function f of x, and this is a well-known cosine function. Cosine function. We write this f of x equal to cos x. Okay. So this same value is repeated here after a period of 2 pi, and you notice this 2 as if there are two ropes. In blind language, these are two ropes. If I pull this rope in this way, what will happen? This will come to this position and I will reduce to this. Okay. Again, if I pull from this side, what will happen? This will also come. So we can change from sine to cos, cos to sine. Okay. What our small child, 9-10 class child read? Sine of 90 minus theta is cos theta. So sine and cos are related by 90 minus theta with a phase 90 degree, or that is called pi by 2. As if someone is waking up at 6 a.m. morning and someone is sleeping and waking at 9 a.m. When someone is going to school, some other is doing his brush. So that's why the sine and cosine are related, and both are the examples of periodic function. Okay. So now let's take the simple example of simple pendulum. Okay, we have seen our watches at home. Okay, so this is the pendulum. The pendulum fixed in the watch. So this is a support. So what will happen? The pendulum, suppose I will drive the pendulum here and leave it. What will happen? It will again oscillate. The same state is repeated after a certain time. So that time is called our period. Okay. In 45 minutes, one class completes. That is called a period. Okay. And you notice, suppose a swing. At the time of Raja festival, we use swings. So that we bring this swing to one side and pull it. Okay. What happens? It also execute a periodic motion. At each interval of time, like 2 seconds, 1 second, 30 seconds, it will returns to same position. So that's why they are called periodic function. So now some other periodic functions are there. This is called square wave. So this has a period. Suppose this is t. After t, the square wave repeats itself. And some other waves are also there, like this, called sawtooth wave. ଓଡ଼ିଆରେ କହୁ କରତ କଳ, ଠିକ ଅଛି। So these are like short tooth করত দান্ত ভଳି দেখা যাচ্ছে ঠিক আছে so this is called short tooth wave at each interval of time the wave repeats so this type of functions are seen in electronics and earlier what we have seen in cosine sine are found in mechanics okay so these are the examples of short tooth wave, square wave, sine wave, cosine wave. I have given you so many examples with physical idea of these periodic functions. So these are well behaved functions. Most of the cases in solid state, in quantum mechanics, in classical mechanics, we discuss the periodic motions. Okay, like sun is maintaining a periodic motion, earth is maintaining a periodic motion. At every morning 6 a.m. we saw the same earth, same sun. Okay, so what does that? That's a periodic motion. In a period of 24 hours 24 ঘন্টারে থরে আমি একা সূর্য দেখুছি ঠিক আছে so that's also a periodic motion. Okay, so many examples you can find all around you of the periodic motion. So now our job is to make it a transformation, a Laplace transformation of this kind of periodic function. So now we will consider a function f of t which is periodic. F of t is a periodic function with period t. That means in each t second, proti t second re, the function repeats itself. We will see the same behavior of the function. So we can write f of t equal to f of t plus capital T. Again f of t plus 2t. Again f of t plus 3t and so on. Whatever time you can wait, we will see after each t second you will find the same functional behavior. So that's the periodic function. So we will find the Laplace transform of such a periodic function. Okay, so Laplace transform of this function equal to, by very definition, 0 to infinity minus st, the function, and so now we will break this into t intervals. In each t interval 0 to t, 0 to 2t, 0 to 3t, I will break this interval so that after each t interval I have the same behavior. So that's my technique of integrating such a periodic integration. Fine? Okay. So what I will do, from 0 to t e power st f of t dt. I will break this interval into t intervals. t2 to t e power minus st f of t dt. Again 2t to 3t e power minus st f of t dt and so on. Adding each t interval, I will go from 0 to infinity. Even I will finish whole my life adding t interval. Okay, every 24 interval adding 365 days. Every year adding my whole life, 60 years, 80 years. All right. So like that, we will reach from 0 to infinity by t intervals. And in each t interval, I have same behavior, same nature. That's my technique. So now, I will have a substitution. Look at here, find first integral. I have written it. Second, t2 to t. I will have a substitution. I will change into a new variable. Suppose this variable is u and I am substituting u is equal to t plus t in second integral. Okay, and you notice what will happen to here at t is equal to t. Well, so in second integral I will change in this way, t equal to u plus t. I have so many kinds of variation, I have so many kinds of substitution. Whatever in our useful way, what will be useful in my calculation, I will do that. Okay, but some other substitutions are also valid, no doubt, but here I will prefer this one because it will easy for my calculation. Okay, that's why. Okay, so in the second integral what I am doing, I am substituting my t is equal to u plus t, where u is a new variable. Okay, so look at here, what about my limit? At lower limit, small t equal to capital T, small t equal to capital T, t will cancel, what will I left with my new variable, that is u equal to 0. So that is 0. At small t equal to 2t, at small t equal to 2t, 1t will cancel, u equal to capital T. Okay, so now this reduces to familiar form as the first integral 0 to t and 0 to t. How is achieved? How is it achieved? By substituting t equal to u plus t. Fine. So e power minus s, in place of small t we were substituting small u plus capital T. So this is small u plus capital T. In place of f of t, f of small t, we will substitute u plus t. And what is my dt? If I differentiate, dt equal to simply du, because capital T is a constant. Okay, so this is du. Done. So complete first integral, second integral, third integral. I will use another technique. So t is equal to u plus 2t in third integral. In third integral, look at my third integral. Here is my third integral. Small t is substituted with a new variable u and 2t. So small t is 2t. When small t is 2t, look at here, 2t will cancel. Okay, what is left with me? U equal to 0. So lower limit is 0. Now at small t is equal to 3t, small t is equal to 3t, put it here, 3t and 2t are balanced, and what is left? U is equal to t, u is equal to t. And see what is in the first integral, what is in the second integral, I am getting that is in the third integral. Fine. Okay, so e power minus s, in place of small t we are using u plus 2t, u plus 2t. So what is left with me now? F of t. So what I am substituting? T plus 2t, f of u plus 2t. And now if I differentiate both sides, what will I get? dut equal to du. So I will substitute in place of dt, du. Okay, so in this way I will continue up to infinity throughout my whole life. Okay, so let's take only 3, and what is the nature, what is the result from these 3, we will generalize into other integrals. Okay, so somehow if I have a fourth integral, what will I substitute? T equal to u plus 3t. If I have my fifth integral, what will I substitute? T equal to u plus 4t. So similarly we will get some other terms up to infinity. So we have only taken into account only 3 terms. Okay, so what is the behavior we will find in 3 terms, we will generalize it into infinite terms. Okay, fine. So we have this much now. So we will use the definition of the periodic function. We will use the property of the periodic function here. So for first, I have no problem. So keep it here. E power minus st f of t dt plus Now you notice 0 to t, this is our objective. E power minus SU is my new variable. What is left? E power minus S and capital T. So that will I write here, S and capital T. Notice in the first term nothing is there, only 1 is there. In the second term I have a multiple. Okay, what is left? F of u plus t. What is that? The function will be f of u. And what is left now? du. 0 to t e power minus s u. So this f of u plus 2t is again f of u due to the periodic nature. So what will be here? E power minus 2s capital T. Okay, plus I have this kind of continuation. Can I write another term? Just another term. E power minus 3st 0 to capital T e power minus su f of u du plus this will continue up to infinity. Alright. So now notice here what is this in the first integral, that is in the second integral, and that is in the third integral. What is the difference? Only here is a small t, here is small u, here is small u, and for each term I have different variables and these are called dummy variables. So I can always replace here x, y, z, here x, y, z, here x, y, z. So it is convenient for me that take every variable same. In every integral I will take a single variable. Let's construct to u or t, x or y, whatever dummy variables present in every integral, we will take the same variable. So let's restrict it to u. Okay, so that is looking good. So 1 0 to t e power minus su f of u du. Fine. Plus what is left now? E power minus st 0 to t e power su f of u du. E power minus 2st integration 0 to t e power minus su f of u du, and so on. This will continue up to infinity whenever we will reach at our higher limit, that is infinity. We have started from the lower limit to higher limit. Now you notice in every term I have same integral. So that is the beauty of the periodic function, that is the nature of the periodic function through which we are easily calculating the integration. Fine. So now if I take common that integral, so in every integral I have a common thing, so that I will write only once 0 to t e power su f of u du. So now what is left in the first term? 1. What is in the second term? E power minus st. What is in the third term? E power minus 2st. This will continue up to infinity. Easily you can tell me what is in the next term. What will be in the next term? E power minus 3st. What will be the next term? E power minus 4st. So that is the nature of periodic function. Well, so we have 0 to t exponential e power su f of u du as it is. What is this? Look at the first term, only 1. Second term, 1 into e power minus st. Third term, again that 1 into e power minus st, a power 2 is there again, and again there will be extra power 3, 4 like this. So what is this? ar square, ar cube. What is this called? A geometric progression. What we have studied in 9th and 10th class. This is a geometric progression. And what is the value? So I am recalling you that a plus ar square up to infinity is 1 upon 1 by a. Okay, where a is called the first term, r is called the common ratio. Look at, in every term 1 power of r is increased, and here also 1 power of e power st is increased. What is small a here? 1. What is our r? E power minus st. So we will have a ready-made formula for that. Let's write 1 upon 1 minus e power st. Okay, so comparing with our geometric progression. Well, so just write it. This is independent of small u. So I can write 1 by 1 minus e power minus st integration 0 to t e power. Now I will take it to small t, because everything we were writing in small t. Okay, so what we have finalized, I can change the dummy indices to my desired form. Okay, so that is small st f of t then dt. Okay, so this is my final result for a periodic function. Look at the initial stage, lower limit is 0, higher limit is infinity. That was looking a tedious way of calculation, but now this is a simplified formula. So every time we will use this formula. Well, so the ready-made formula for this periodic function is 1 upon 1 minus e power minus st integration 0 to t e power minus st f of t dt. So this is the ultimate result for Laplace transform of a periodic function. Okay, and this function is periodic in nature. And how much it is period? Capital T. The period is capital T. Okay, so this is the ultimate result. We will see applying through a problem. Come to the question, application part. Find the Laplace transform of a function like this. I am writing the functional behavior t, and another thing is there, pi minus t. T is from 0 to pi, and next pi minus t is pi to 2 pi. Well, the function is designed in this way, and you notice this is a periodic function. How this will be a periodic function just by mere inspection? Let's plot it. If I plot, here is my abscissa, here is my ordinate. From 0 to pi, let's choose 0 to pi. 0 to pi. Here is 0 to pi, and again pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi. Okay, so what is the value of the function 0 to pi? That is t. Like y is equal to x. What is this? This is popular straight line. Okay, y is equal to t is a straight line passing through origin. So I will draw this straight line from 0 to pi. Okay, so What is my maximum value? That is also pi. Let this be here. Here is the maximum value pi, that is 3.14. Okay, so up to this, like this. Okay, pi minus t from pi to 2 pi, pi minus t. So every time this is a negative slope graph, negative. Pi minus t means it will less from pi. Okay, notice here this. Again from 2 pi to 3 pi it will also increase. Again from 3 pi to 4 pi it will decrease, as if a tooths of the saw, କରତର କଳ ଭଳିଆ ମୁହଁ ଭଳିଆ ଦାନ୍ତ ଭଳିଆ ଦେଖା ଯାଉଛି, ୟାକୁ ଆମେ କ'ଣ କହୁ? ସॉ ଟୁଥ ୱେଭ୍. This is a saw tooth wave. If I continue like this is a sawtooth wave, and I have introduced that the sawtooth wave is a periodic wave. If you see the saw, तम दी करतटा को देखिबो केमती हबो, प्रति इंटरवल रे रिपीट हुए, से दांतटा प्रति इंटरवल रिपीट हे जाउथे, राइट. द tooth of the saw is repeated in every interval. That's why this is a periodic function. So we choose this formula for our better application, better calculation. We will choose this ready-made formula. We will not go for this entire procedure. We will remember this and we will calculate the Laplace transform. Well, we have seen the beautiful sawtooth diagram. Okay, so now we will calculate the Laplace transform. This f of t equal to 0 to infinity f of t e power minus st dt is the definition for Laplace transform, and that is reduced to 1 upon 1 minus st integration 0 to t e power minus st f of t dt. Okay, where what is t, after which time, what time the function repeat itself from the figure, t equal to 2 pi. So what sawtooth I have shown you in the picture, you notice that after each 2 pi the tooth repeats itself, the triangle repeats itself. Okay, so now my t is 2 pi. So this t, capital T, period of the function, the interval after which the function repeats is 2 pi. So now we will substitute that 1 upon 1 minus e power minus 2 pi s. Done this part. 0 to 2 pi e power minus st f of t. F of t has two values. So we will write this f of t as it is and replace it later. Okay. So now this is 1 upon 1 minus e power 2 s t. Done. From 0 to pi, this is a different form, that is small t, e power minus st small t dt. Done. Plus another interval, choose another interval. How much is that? Pi to 2 pi. From pi to 2 pi e power minus st, the functional value is pi minus t, pi minus t, and well, so 1 by 1 minus e power minus 2 st. Then we will calculate explicitly what is here, t e power minus st then dt. Limit is from 0 to pi, okay, plus pi to 2 pi, then this is of two functions. So pi minus t e power minus st dt. All right. So now I will close my bracket. Now what is here, that is fixed, 1 minus e power 2 st. Okay. So now you notice this one, two forms are there, two functions are there, we will use by parts. So from by parts, well, for by parts we will choose e power minus st as our v and t as our e. So let's keep this t, e power minus st, integration variable is s, well, and evaluated between 0 to pi, minus derivative of first function, t derivative is 1. So again integration of this is e power minus st divided by minus s, okay, and again there is a integration 0 to pi. Done. First term is over. Second term, and you notice that second term has two terms, so that is pi to 2 pi, pi e power minus st, then minus that is again pi to 2 pi t e power minus st dt. We will calculate, evaluate it, 1 minus e power minus 2 st, okay. So now you notice here minus is there, that is why I am choosing lower limit, okay. So if I choose my lower limit first, so this will become 0 and this is 1, so this is 0, okay. So now minus upper limit is pi, pi e power minus pi s, okay, divided by s. Done. This much, minus and this minus become plus. So again this is a simple integration. What is that? E power minus st divided by, how much is that? Here is a minus s, this minus minus we have already taken, so let us keep it a single s and square. So this will be evaluated between 0 to pi, plus this pi is here, e power minus st divided by minus s, evaluated between pi to 2 pi. Done. Again this will follow the by parts, minus t is there, e power minus st is there, evaluated between pi to 2 pi, okay. So again there will be another term, minus minus plus. So first derivative is 1, e power minus s, okay. So integration variable will be s square, okay. So minus is pi to 2 pi, okay. So now this completes, okay. There are different terms, we will calculate these terms, each and every term we will evaluate the upper limit and lower limit, and we will find the simple answer to the Laplace transform of the sawtooth wave. So thank you everyone.